Okay, lecture 66, titled Pre-Newtonian Physics. It's a warm summer evening, circa 600 BC.
You've finished your shopping at the local market, or agora. And you look up at the night sky, and there, you notice some of the stars seem to move, so you name them Planet Ace, or Wanderer. Yes, Penny?
Does this have anything to do with Leonard's work?
This is the beginning of a 2,600-year journey we're going to take together from the ancient Greeks, through Isaac Newton, to Niels Bohr, to Erwin Schrödinger, to the Dutch researchers that Leonard is currently ripping off.
Well, in the coming weeks, we'll get to Newton anyway. Probably not the researchers that Leonard is ripping off. So the ancient perception that simple mathematical principles are at the core of natural phenomenon is as prevalent today as it was back then in Greece. So what are these mathematical principles that I speak of? So let's first talk about Pythagoras, circa 500 BC. Pythagoras' belief was that the motions of the planets were governed by ratios of whole numbers. He called it the music of the spheres. So you might remember, if you've studied a little bit of music theory, right? How whole numbers are relevant to music theory. Yes?
Yeah.
Look, a third and a fifth and all that. What do you call the table of fifths, I think? So these whole number ratios were very important to Pythagoras. And in fact, there was a young mathematician that worked with him named Hippasus, who had some crazy ideas about irrational numbers that he brought up with Pythagoras. So these are numbers that cannot be represented by whole number ratios. And to speak of such numbers is, of course, heretical, I guess would be the right term. So Pythagoras rowed him out into the Mediterranean in a boat and threw him out of the boat and murdered his ass. At least that's the story we're given. So he took it very seriously. The very first model of the solar system was from Anaximander, and he had a geocentric model of the solar system. That means with the Earth at the center of everything. So he thought that everything moved around the Earth. Okay?
All right.
Now he did have at least one interesting explanation for the seasons. So he would imagine this ring, which the sun would move around, and then here we'll have the Earth, where I'm indicating it's kind of rotating. Here's the Earth rotating, and we have the sun over here, right? Its rays are incident on the Earth, and here the ring is above the Earth. And then later, this would be during the summertime. During the winter time, however, here's the Earth rotating. The ring would now be below the Earth, such that the rays of the sun are incident on it at this lower angle, you see?
Yeah.
Now that is actually the reason for the seasons, that the angle of inclination of the sunlight, right, changes during the summer and the winter. And just sort of a curiosity. During the month of January, which is kind of the high winter month, right, where do you think the sun is relative to the Earth? Do you think it's at its closest point or its farthest point? Well, that was fast. Somebody must have read this somewhere, because that's the correct answer. Most people would say, oh, it must be farther away since it's winter, it's cold. Of course, they forget that down in South America, it's summer, right? So it all has to do with the tilt of the Earth and where the sunlight is hitting you from. So if you're tilted like this, right, the sunlight is hitting you at this very shallow angle, whereas in summer, it's hitting you more directly on, right? That's why the sun appears so high in the sky in the summer and so low in the sky in the winter. Anyways, so he at least had some aspect of it correct. Contemporary with these two guys was a competing theory. It was actually the very first heliocentric theory of the solar system by Aristarchus. He also, there are no extant works of Aristarchus that I'm aware of. I think we know about it through Archimedes. Archimedes had a work called The Sand Reckoner, and in there he mentions Aristarchus and his heliocentric model. He also mentions that Aristarchus was aware that the stars were really just like our sun, except much farther away. And he realized that we would not be able to perceive it as such, because it was so far away that parallax would be impossible to measure. Okay, so what is parallax? Anyone know what parallax is? No? Well, if you look at a distant object with your eyes, and then you close one eye, right?
Yeah.
And then close the other eye, the distant object will appear to move, right?
Yeah.
So let's say here is the sun, and here is the Earth at two different time periods. And so we can pick a couple of points, and we'll pick some distant star way over here. Maybe it's Proxima Centauri, right? That's the closest star to us. And if we look at it, say, in the month of, I don't know, call this like September or something, right? We look at it in September, right? And then what's the complement of that? Let's see. Maybe April or something like that would be over here, right? And we look at this distant star, right? And make a line of sight to it. It means about here, right? And then we were to measure the same, look at the same star, right? At a different time, there we go, right? We would find that when we looked in September, you know, the star looked to our right, so to speak, right? To the right of the position that it does with respect to when we look at it in, say, April, when it appears to the left, okay?
Yeah.
You see, so we're looking out, it's to the left, we're looking out, it's to the right. You know, some central point that we're using as reference, right?
Yeah.
And so we can measure this angle, right, that's subtended by this, by how much we look to the right versus how much we look to the left, right? And we know what this distance is, right? We define the distance from the Earth to the Sun as 1 astronomical unit, AU, okay?
All right.
So at least you can figure out how far away something is using parallax in units of astronomical units, right? So whatever the distance from the Sun to the Earth is, that's 1 AU. We can figure out how far away this thing is if we can just measure it. Today we can measure pretty accurately using modern telescopes, okay? And I think, what is I wrote it down, let me see. It's something on the order of 4 times 10 to the minus 6 radians, okay? And so we can use a couple of things we could do if we wanted to. We could divide this and make a couple of right triangles out of it and use trigonometry to figure out what this length is, given that we know this length, right?
Yeah.
Or we could use S equals R theta, right? As long as theta is small, this will be a fine approximation for this chord right here, right? And if we do that, what do we get? We're going to get, so if we call this angle, let's just do this, we'll call this angle theta over 2. The sine of theta over 2, that's going to be equal to what? So here's our right angle here, right? So the sine of this angle will be equal to the 1 AU over this distance r, which is the distance of the star we're interested in, right?
Yeah.
So we can solve for r here, right? That will give us r equals 1 AU divided by the sine of theta over 2. You just take this number 4 times 10 to the minus 6, half it. Even at this size, right, the theta is approximately, the sine of theta is approximately equal to theta, right? So it's approximately equal to 2 times 10 to the minus 6. So it's like 1 over 2 times 10 to the minus 6, which turns out to be approximately 250,000 astronomical units, okay? If I convert that into light years, right, that comes out to be approximately 4 light years, which is on the right order of magnitude, okay?
All right.
Yeah. So that is parallax. So after Aristarchus, you thought, oh, well, that heliocentric idea must have been a good one and it caught on since it's the correct one. But no, Aristotle was in favor of a geocentric model of the universe. Okay, so 4th century BC, Aristotle doubled down on the geocentric model. Okay, he added a few extra things to it. He added this idea that the stars were basically a sphere, right, a spherical shell, right, outside of our solar system. And so you can think of it as some shell that's got a bunch of little bright spots on it, or you can think of it as a curtain with little holes poked in it. There's a big light behind it. He gave one more shell outside of the shell that corresponded to the stars. That was the prime mover shell. So this is the the origin of first causes, right? It's the chicken or the egg problem, right? If something causes something, it causes, if the chicken makes the egg, which makes a chicken, which makes an egg, which came first, right? And so Aristotle's answer to this was the prime mover, right? This is the thing that starts it all off. You could think of it as his conception of God, all right? So he put the prime mover shell just outside the star shell in his geocentric model. Now, I don't mean to impugn Aristotle, but a lot of wrong ideas that took a long time to correct. If you were to go back to Aristotle and show him a helium balloon, I don't think he had anything of this nature back then, he would have been like, exactly, that's the best illustration of the laws of physics I've seen to date, because his belief was that heavy things move towards heavy things and light things move toward light things, and so helium balloons being light, they go up to the ether where everything is lighter. So he believed that all the heavy stuff was like Earth was like the place where all the heavy stuff is, and everything that's heavy wants to get there. Things that are light want to go up to the light stuff. So he believed in these two different spheres, this kind of terrestrial sphere, right?
Yeah.
And this celestial sphere, right? So he believed that the stuff, the planets and the stars, right, were special material, lighter material, okay?
All right.
And that's why they were where they were. This disconnect between terrestrial and celestial is important, okay? And it dominated scientific thought for well over 1,000 years, right? Yeah, he also believed very heavily in the same kind of ideas that Plato had, right? About there's these ideal forms, and then there are these imperfect manifestations of ideal forms. So like every horse aspires to be like the ideal horse, right? Which is like the epitome of horseness, right? and every real horse falls a little bit short of it, right?
Yeah.
And so circles for them, right? It was, without a doubt, the motions of the planets must move in circles. Everything must be in circles. That's what these spheres are all about. There's a sphere for Mercury. They only knew of 6 planets back then. So Mercury, Venus, Earth, of course, and would be Mars, and then Saturn and Uranus. Okay? No, Jupiter, sorry, not Uranus. Saturn and Jupiter. These are the ones they knew of. These are the ones that you can see with the naked eye. Okay?
All right.
Now, of course, the Babylonians, right, well, really the Sumerians, right, were seeing stars. The Egyptians were seeing stars. And planets as well, right? They knew how to track these things to figure out times of year and stuff like that, to plan for harvests and whatnot. But then none of them had the same kind of abstract, mathematically backed logic that the Greeks developed, right? So we owe most of our Western heritage to the Greek thought. But it had its origins, I think, in the more concrete, applied thought of the Sumerians and the Egyptians. Okay, so everybody makes a contribution. So we jump forward a little bit to 2nd century AD, to Ptolemy, another Greek. He also had a geocentric model for the solar system, but he added this thing to get the motions right, because they're always trying to track the motions of the planets, right?
Yeah.
To know the time of year and stuff like that. And also astrology was a big thing, I think even back then. But they weren't exactly, the tables that they would record, they weren't very precise. Okay? It was hard to predict these things. So they assumed these circular paths and whatnot. And so what they had to do, he used the retrograde of Mars as the basis for what he called epicycles. Okay? And I'll try to demonstrate that here. If we look up at the sky at night and we go outside on successive evenings, always at the same time, and we look at Mars, we're going to see it moving across the sky. It'll move across the sky, and it'll do something like this. And then it'll kind of start to slow down. And it'll turn around again, and it'll kind of shoot off like that. So this is just observation of different nights. So it's moving across the sky a little bit each night. And then it seems to reverse course, right?
Yeah.
And then come back around again, right? And so this was called retrograde. And so Ptolemy's explanation for it was if we were to draw the orbit of Mars, it would always have this, what he called epicycle. So if this is its orbital direction, I guess maybe the epicycle goes this way. Right, so it's also going around a little circle, so it's circle on circle. And this, from an observational point of view, supposedly, well, explained to them the retrograde motion of Mars. Okay?
All right.
Epicycles were invented to explain retrograde motion. But he added them to everything to get so that the tables were predictable. Okay, so they could predict where they would be in the future. So let's jump ahead roughly 1,000, 1,100 years to Copernicus. Where did my eraser go? Here it is. Jump ahead to Copernicus, who had another explanation for the retrograde of Mars. Okay? So there's 2 nice things about Copernicus. One, he's finally giving us a heliocentric model of the solar system, which is, of course, the right model, a heliocentric. But he still has the circular orbits. Okay?
All right.
And how he would explain the retrograde motion of Mars is like this. So I'll draw, this will be the Earth orbit, and then I'm going to draw the Mars orbit, not to scale, obviously. Do my best anyways. It really only matters on this side over here. And so I'll pick a couple of points for Earth, something like this maybe. So what I've done, I've tried to make the length, so I'm drawing the position of Earth during equal time intervals, okay? So, to indicate the speed of the Earth. And I'm going to draw Mars. So he said you can explain the retrograde motion of Mars if you assume that the orbit of Earth is faster than the orbit of Mars. So if we're moving faster than Mars is moving, then we can explain the retrograde motion. And here's how. So so from Earth, right, line of sight, we would see Mars at some point like this. But Mars, I'm going to draw equal time intervals for Mars, but it's going to be going slower. So it's not moving as far, which means that the distance between the points here will be closer together. So I'll use that distance there, I think, if I can stick with it. I may have to adjust it a little bit for the picture to make any sense. But you can see, right, that Earth is moving faster because if these are equal time intervals, right, the distance that Earth has traveled is a larger distance than what I've shown Mars to travel, right?
All right.
So then we look at this later time. We'll see it like this. And then we look at this time here. Now it's over here. This one is probably a little bit off. You see
Yeah.
what it's doing? And then finally it's going inside. You should have drawn more points in, but it's kind of going around like this where we see it. And then it's going to circle back around and then go on out, right? So its position is changing, right? And we can explain that because it's not the best illustration. I'll try to put on the video, when I put the video up, I'll try to put a picture. It's a better picture of the Ptolemy's, Copernicus's retrograde explanation than this one. I have a nice picture that'll show it a little more clearly. I just drew this on the fly. It's a little hard to do. We didn't need epicycles to explain the retrograde of Mars. Could do away with that. Okay? So we've kind of moved into a more modern era, right? But it's worth reflecting that Greek thought, it's worth reflecting that the Greeks taught us that the truth is not always obvious. That only trained human reasoning can help us understand the underlying mechanisms of nature.
All right.
So we kind of move into what I would call modern science now. I want to read something from Galileo Galilei, who lived from 1564 to 1642. This is a quote. "Nature is written in the great book, which ever is before our eyes, I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. The book is written in mathematical language, and the symbols are triangles, circles, and other geometrical figures, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth." Right, so this is kind of reminiscent of Plato's allegory of the cave. But it's also important to note, right, these symbols, the triangles and circles and whatnot, right? Because when we finally do get to Newton explaining Kepler's laws, right, we're going to do it in the way that he did it, geometrically, okay? Today, anyone that treats it in, say, a college physics course or something like that will use the full arsenal of tools from calculus that make it easy to demonstrate all of this stuff. But we're going to look at it the way that Newton looked at it. At least we're going to try to. We may have to do a little bit of hand-waving here and there because we don't have time to go through all of the details in the Principia. Principia. That's his book. Yeah, any question?
No.
Oh, I thought you were raising your hand.
I'll just start with this, I guess.
Oh, okay. But let's talk about Galileo for a minute. So, I guess Galileo was probably the first person to really take down Aristotle, right? Aristotle thought that the celestial matter was like perfect in every way, right? And so Galileo gets access to a telescope. I forget who invented the telescope, but Galileo was the first one to build one and look through it at the stars. And he looked at the sun, in fact. Right? He obviously put a filter on there, and he saw that the sun was not this perfect solid object. It was actually quite marred, right? It had spots all over it, right?
Yes.
And so that was a problem. But that wasn't the biggest problem. The biggest problem was that under the geocentric model, the whole point behind the geocentric model was that everything revolves around the Earth, right? And Galileo it was easy for him to show that that's simply not true, because if you look at Jupiter with a telescope, Jupiter's got moons. And you can see them. They're orbiting Jupiter, not the Earth, okay? You just have to look at it over a few nights and you'll see what they're doing. They're orbiting Jupiter, not orbiting Earth. So, yeah, it completely destroyed the old Aristotelian view of the cosmos, so the celestial sphere. But his mathematical contributions, anyway, right, were with regards to terrestrial physics. Okay, the physics of things on Earth, which even at this point were believed separate from the physics of the stuff in the up in the sky. All right, so Galileo, the mathematical work that he did and the experimental work he did really had to do with terrestrial physics, right? The physics of stuff here on the ground. You probably remember his inclined planes, right? So we start the ball off up here. Where each of these moments that I've drawn up here, right, are all a single delta t, or a single time interval, right? So during the first time interval, right, the ball travels a distance of 1. During the second time interval, between here and here, travels a distance of 3. Between the next time interval, travels a distance of 5. And so if we were to make a table of this, right, we might say, okay, well, alpha times d at 0, that's the time, is equal to 0. That's where it starts out, at the top at 0. Alpha, which is just some constant, right? Some constant times d at time 1 is equal to 0 plus 1, which equals 1. And alpha times d at some time 2, that's the second time point here, right? Here's the 0, here's the 1, here's the 2, right? That's equal to 0 plus the 1 plus the 3 that we the 3 units we traveled during the second time interval, right? What's that add up to? That adds up to 4. And then alpha times d for the third is 0 plus 1 plus the 3 plus another 5 we get in this third time interval, giving us 9, right? This is 1 squared, this is 2 squared, this is 3 squared, right? So from this we can glean that the distance traveled as a function of time, right, is equal to, and if you work out what the constant is, right, you can get this to be equal to 1/2 a naught, a constant value, times t squared. Of course, a naught, the value of the acceleration, the constant acceleration you're experiencing, depends on the angle of incline. Okay, we're not going to worry about the details of that. It's the fundamental relationship, the square of time relationship was Galileo's big contribution. His other big idea, right, was the following, right? So if we imagine, here's our incline, okay, and then we put up, another ramp. Maybe it's got a smooth curve, whatever. It goes up like this, right? And we'll notice that if we drop the ball from here, it's going to roll down the hill, and it'll roll back up, and at some distance, it comes to rest and then reverses course, right?
Yeah.
And so he would have called this second ramp a retarding force, okay?
All right.
He would have called the first ramp, I guess, accelerating force, something like that, okay? So he was interested in the question, what happens to the ball in the absence of a retarding force? And so the way he thought about that, he said, okay, well, I look at, these ramps, I put this retarding force ramp at the end of the track, right? How long does it take for it to come to rest, right? Well, depends on how steep the ramp is, because if I were to change the ramp out, right, to something like this, right, it's not going to come to rest for quite a bit. It'll travel quite a bit farther before it comes to rest, right?
Yeah.
Now, realize that we have the benefit of conservation of energy, right? We know what's going on here. He did not, okay? So this is probably harder for him to see than it is for us. But you can see that as we make the ramp less and less steep, right, we're reducing the retarding force, and it takes a longer period of time before the ball comes to rest, right?
Yeah.
Because it has to travel farther before it gets back up to that height, right? It's still not there, so I've drawn it, right? It could be somewhere over here, right? Because it has to rise back up to that same level because of the potential energy of the ball initially, right?
Yeah.
He didn't know that, of course, but he did know that if he made the retarding force less, it took longer and longer and longer. So he thought, well, what about the limit, right, of if it's always taking longer and longer and longer, what if I let my retarding force be 0, so there is no ramp, right? Then how long does it take for it to come to rest? It never comes to rest. It takes forever, right?
Yes.
So it's just a trend that as we decrease the angle of the retarding ramp, the time it takes for the ball to come to rest is longer and longer and longer. And if we take that out to a retarding force of 0, right, then the time that it takes to come to rest is infinity. And so this is how he composed his principle of inertia, okay? That objects at rest stay at rest, objects in motion continue in motion, okay?
All right.
It was this experiment here. Aristotle, right? Aristotle would have said that the force is equal to v, the velocity, right?
Yeah.
Galileo, I think he only has one L. Galileo, F is equal to delta V. Really, this should be proportional to, I suppose, right? Right? Force is proportional to the change in velocity, okay? So it changes the state of motion. All right. So that brings us to Kepler. Johannes Kepler was a German. No, he's German. He's German. Johannes Kepler, 1571 to 1630 were his dates. His mentor was a royal imperial. I think that's too many. He was a Danish imperial astronomer, right? His name was Tycho Brahe, and he was world renowned. He was absolutely hands down the best naked eye astronomer ever. Okay, he had a lifetime of data. I think they call them Rudolphine tables that he had constructed over the course of his life. He actually wanted to undo Copernicus and go back to a geocentric model of the universe. And on his deathbed, he even asked Kepler, please use this data to prove my geocentric model of the universe. I don't know what Kepler said, but obviously he did his own thing. He recognized Kepler as mathematically very talented, which is why he gave him the data in the first place. It was a different time back then. This was before the time where we share information to advance science, right? This is a time in which you hold on and safeguard information, right? Think of the battle between Cardano and Tartaglia, right? They held on to secrets. They didn't want to get them. That's how you got positions and stuff like that, by having this data all to yourself. Yeah, all right, so But yeah, he did not use it to try and prove a geocentric model of the solar system. What he did instead was he cataloged his observations in what we now refer to as the Kepler's three laws. Okay, so I'm going to go through them quickly here, and we'll talk about them in more detail when we get to when we start talking about Newton. Okay,
All right.
I'm going to do another lecture where we talk specifically about ellipses. Okay, because law number one. I should write Kepler on the board, right? Kepler. Law number one. Planets move in elliptical orbits with the sun at one focus. Okay? I think you all know generally what an ellipse is, yes?
Yeah.
I'll do my best to draw an ellipse. That's not great, but it'll do. Take a circle and you squash it a little bit, or you stretch out on one side, right?
Yeah.
That's an ellipse. So why would this be the case, right? What's going on here with this? I'm not ready to talk about that yet. So yeah, this is an ellipse, and you can construct an ellipse. If you imagine you've got a circle which has a center point, right?
Yeah.
Now make it two center points that are on top of each other and start stretching them out, right? And as you stretch them out, these two, what we call foci, again, I'm going to do a detailed talk on ellipses tomorrow. And the kind of the defining quality of an ellipse, right, is that the distance from one foci to any point on the ellipse, right, and then to the other foci always remains constant, right? So a really nice way to construct this is to get a couple of tacks and stick it into a piece of paper and tie some string around it. Get a pencil, right, and just trace out the ellipse with the strings guiding the pencil around. I encourage you to do this as an exercise. Maybe I'll put in a little video snippet of this in action, okay, in the video so you can see it. But I should have thought to maybe bring something to do that demonstration. It's not hard to do. That's how ellipses are made. So that's law number one. Not circular orbits. They're not circles. They're ellipses, okay? Two. Planets sweep out equal areas in equal time. What's that mean? It means if I draw my ellipse, okay, I put my sun here, let's say, here's the sun, and I look at some time interval, okay? When say the Earth is going to travel from here to here, let's say it's going this way, in this time interval. And then I sweep out, I look at the area that it's swept out here. See that area? Yeah?
Yeah.
And then I look at another time interval of the same duration, so say 10 days, 2 weeks, a month, something like that, right? But I look at it over here. What's it look like over here? Well, this law is saying that the area will be the same, right? So here we are. This area and this area are the same, which means that the planet is moving faster over here than it is over here. You see?
Yeah.
Because the arc that it's made is bigger because it's moving faster, okay? So does that make any sense? Well, I need to draw another ellipse here. Let's think about what's going on. We know in the end where this is kind of going, right? If this is the sun, and let's put our planet here, and let's say we're going that way, right?
Yeah.
We know that there's going to be this force between the Earth and the sun, a force of attraction we call gravity, right?
Yeah.
And so this force is in the line, the force is in a direction on the line connecting the two bodies, okay? So that means, here's the line connecting the two bodies, right? That means the force is going this way. You see that?
Yeah.
If I'm traveling this way and I have a force that's pulling me to some degree in a backwards direction, what's it doing? Is it speeding me up or slowing me down?
Well, slowing you down.
It's slowing me down. So I'm slowing down on this leg of the journey. What about over here? What's going on over here? Now, my velocity is that way, right? Here's the line connecting these two bodies, which means that the force is in this direction. Now what's it doing?
Now it's speeding you up.
It's speeding me up, right? So when I'm on this leg of my orbit, I'm getting slowed down, right? As soon as I get around this bend here, right, I start speeding up again, you see?
Yeah.
Yeah. So that's what this equal area in equal time business is about. It's about the fact that the Earth is traveling faster, right, when it's over here, and then it starts to slow down, and it'll be at its slowest over here, you see?
Yeah.
And then his third law, and this, but the second law is pretty easy to prove. We'll prove it two ways, right? One, using some of the angular momentum tools that we learned recently, and the second way we'll do it is just geometry, okay?
All right.
Well, the third one, I'm not going to write it out in explicit detail. It says the cube, let me read it to you. The cubes of the mean distance of the planets from the sun are proportional to the squares of their periods of revolution. That's a mouthful, right? But what it says is that the period of a planet squared is proportional to, we'll call r the mean distance from the sun, r cubed. Now, which of these three laws would you think Kepler would claim to be his greatest achievement? The first law, the second law, or the third law?
First.
You think, I mean, if I were looking at this, I'd say, that first law is pretty significant, right? The fact that it's an ellipse and not a circle like everyone thought for so long.
Really?
No, he would have definitely said the third law, right? Why? Well, because to him, it was the proof of the existence of God, right? The fact that there was this relationship between the period, and it's this 3/2 ratio, right? This perfect 3/2. It's not 3.1 over 1.42.
Oh,
It's
yeah.
a perfect ratio, 3/2, right?
Makes sense.
And so, to him, this was like the big thing. This was like world shaking for him. Okay. Now he had these theories about. He had an explanation for all of this, and it had to do with Platonic solids, but I can't remember exactly how it went. There are 5 Platonic solids, and I don't recall exactly how it goes, but it's not important because it's not correct. But anyhow, so that is Kepler, and so this takes us right up to about 100 years before Newton is going to look at this data and understand it completely and come up with a model that changes everything. All right, so that's all we're going to say about pre-Newtonian physics since we got up to Newton. Okay?
Okay.